Hi all, my name is Himanshu. I'm currently a fourth year dual degree student in the Mechanical Engineering Department of IIT Kharagpur. And this video is a report submission to my term project in the course Vibration and Noise Control. So the very first part of the term project is the reproduction of this particular paper. This is a paper by Professor Anand Das Gupta at IIT Kharagpur. He is also the course instructor for this Vibration Noise Control course. I've reproduced some of the results from this paper. In this paper, uh, the author has basically found the effective properties of this particular lattice. In this paper, the author has found the properties through FEA as well as numerical and analytical calculations. I've reproduced the part of FEA so that I can validate the FEA model when I later use it for further extension of this work. He has considered this unit cell and written this strain energy in these two beams, and from there he has found the effective properties for the analytical calculations. For the FEA part, he has just built that model in COMSOL and applied some loadings and found the strains and then related those strains to the stresses. I'll try to first show my COMSOL implementation. So here is a COMSOL model to calculate the effective properties of the lattice. I've considered a 31 by 31 lattice as is done in this paper. So to obtain the properties of the effective properties of the material, we need to consider at least three load cases. Here the author has considered these four cases, and I've considered the same four cases. For the first case, and by the way, to obtain the effective properties, to obtain this particular matrix, the lattice material must be known. Although the author has missed that detail in this paper, and but the material that he had used is that steel with these properties. So to match these results, those properties must be known. The remaining results are presented in non-dimensional terms, so the remaining results are fine. But for this particular matrix, those properties must be known. So for the first case, these node points are subjected to force in the x direction of magnitude 10, and these points are constrained in the x direction. With this, we obtain the results like this, which matches quite well with the results given in the paper. After doing this for all the load cases individually, we need to find the strain in the lattice. For this, we need to consider four fiducial points on the lattice and obtain the displacements at those locations so that we can find the strain. So this particular thing, I'm using MATLAB for that. First of all, these are the four points shown by this blue dot. So to obtain the displacements, I'm using COMSOL live link for MATLAB, which basically interfaces MATLAB with COMSOL. So it will first read the particular file, then obtain the displacement and the original coordinates of those locations. From there, we can find the strain for this particular case. I'll show this strain. and compare it with the given in this paper. So this is the one we are looking for, and we can see it matches quite well with the paper. Similarly, we do this for all the four cases to obtain the individual strains, and in this file I am obtaining the properties. So it will read the individual MATLAB workspaces and obtain the strains, and these are the stresses are calculated based on the loadings that I have applied in my COMSOL model, and is also given in this paper here. This procedure is also described very well in the paper. So let me show the properties. This is what we obtain. This what I obtain, and this is given in the paper. So we can see it matches quite well in the paper, thereby validating my FEA model, and I can use it later for doing further analysis on the lattice. Having validated my COMSOL implementation, I'm finding the natural frequencies of this lattice when the bottom nodes are all fixed. I'm using the eigenfrequency study of the COMSOL. So here is the first mode shape and the first natural frequency. The second one, third, and so on. Here are the displacement, the U and V displacement along. I'll show where I'm plotting it along this line and this line. So this is along X and this is along Y. Then the top edge. All of these are for the first mode shape. Similarly, we can change the mode shape and see how it changes. Now I'll use the effective properties to make a continuum model in COMSOL. So instead of having lattice, I'm using the effective properties that I had just calculated. So the first mode shape is this, and the frequency is 0.73. Frequency that I obtained from the lattice was 0.71. So these are also matching. Now, but using the effective properties, we can find an analytical solution to the problem. For this, I am using MATLAB. I'll show first the formulation. Now, here is the complete formulation, which I've written in terms of mostly matrices, so that it is easy to be implemented in MATLAB. U1, U2, or U and V denote the displacement components in the x and y direction. Psi are the prescribed functions that must satisfy the essential boundary conditions, and AIs and BIs are the unknown time dependent variables that we need to solve for. So this is pretty straightforward everything, but I've just written it down so that I can write it in MATLAB. After obtaining this equation, IQ is the vector containing the AIs and the BIs. We substitute for Q by this, and then for this to have a non-trivial solution, this must be true. Here is the implementation of this formulation in MATLAB. I'll go through this step by step. Order x and order y denote the order of shape functions or the approximation functions in the x and y directions. And here I am forming the shape functions. This is specific to the boundary condition that I have imposed, which is that the bottom surface is fixed. Apart from that, everything can be used for any other boundary conditions as well. I'll show this shape functions. So for me, the since the bottom surface is fixed, I must have y starting from y raised to 1, so that at y equal to 0, I always have 0 u and v's. Psi x is the okay, pretty straightforward. This s and r vector, everything what it denotes is given in the formulation. This had basically written so that it is clear to me as well what I am doing, so that I don't have to document it in the code. Here are the components of stiffness matrix. This is the C matrix, the numerical C matrix that I that is given in the paper, and these are the other parameters, the numerical K and M matrices. From there, we calculate the eigenvectors and eigenvalues. Then I'm writing it to a text file, these eigenvectors and the natural frequencies. Now I'll make a plot of that. So in this function, I'm basically comparing the results obtained from COMSOL and MATLAB. This U mode shape and V mode shape are the mode shape obtained from the MATLAB results that I had shown, and this is the data from MATLAB. I'll show this plot first. So this is the U and V displacement from COMSOL and MATLAB along y equal to h by 2 line for the first mode shape. Then this is along x equal to L by 2 line, and here are the natural frequencies. So we can see the first 5 or 6 frequencies are matching quite well. After that, the results are diverging. Next, I'll show an animation. Here I am animating the results that I've obtained from MATLAB. I'll just run this. This is for the first mode shape that I obtained from MATLAB. I'll show all the animations. This is the first and second mode shape. Left hand side is for MATLAB, and this right figures are from COMSOL. So this is the MATLAB results are able to capture the mode shape quite well. The natural frequencies are also matching, but okay. But for higher mode shapes, MATLAB is not able to capture the capture all the details. Like for example, here this and this are not so pronounced in the MATLAB results. Similarly, this variation and this variation are not so close, although the natural frequencies are still quite close. For even higher mode shape, the natural frequencies are also getting worse. And so, if we want to obtain a match for higher mode shape, we need to increase this order of the functions here, order x and order y, and this will probably lead to a better match. So to summarize, in my vibration and noise control term project, I have reproduced some of the results from this paper to calculate the effective properties of the lattice. Then I have used that FEA model that I had used to reproduce those results to calculate the eigenfrequencies of the lattice. After that, the effective properties I have used to find an analytical solution in MATLAB, and I have compared the two solutions obtained from COMSOL and MATLAB. Thank you.